Hello, I'm Johannes, VP of Code Security at Sonar, and I'm going to talk about code security in the AI area. We will be covering the state of code security, where we are at. Then we look at how Sonar is approaching this challenge today, and then what are the capabilities in SonarQube to support this. I will show some demos and also give you a sneak peek on what else we're working on before I jump to a summary. Let's dive into the state of code security. So we released a report here, a research study where we covered almost 8 billion lines of code from 1 million developers that wrote code in 40,000 different organizations, right? So quite a diverse set of code in different programming languages, and with 400 million code issues that we studied here. And one finding was that almost one issue every 800 lines of code appears, right? That accounts to 1 to 2 security issues per developer per month. And you can see that's still quite a lot of security issues. When we study the top security issue categories, you can see that still the issue types that you have been seeing in the last decade are fully present. Log injections, cross-site scripting, SQL injections, hard-coded secrets are among those security issue types. And now, as we talked about previously, right, the AI accelerates this challenge. With AI, we are writing more code, we are writing code faster. And so if you extrapolate the statistics now for all this code that is written on top of that and written faster, we will see much more issues, and we have a higher need to make sure that this code is actually safe and can be trusted. So why is AI adding additional gasoline to the fire here? It's because AI is not free of security vulnerabilities, right? LLMs are getting better, but still we are seeing that hard to find risks like security vulnerabilities are added by Gen AI to code. We also see hallucinations, right? Good examples here are the slop squatting bugs, where AI introduces references to libraries and dependencies that you use that actually don't exist, and then attackers can register them and take over your code. And then we also see that code is less efficient. That means the leading LLMs are solving programming tasks very well, but they are writing more verbose lines and more complex code, and that is a security problem because now this code is harder to maintain. More lines of code means potentially more issues. And also, if you want to fix a security issue, it will be harder if this is more complex code. And on top of this, the challenge for organizations now is that you have security compliance regulations that you have to comply with, right? We have the Cyber Resilience Act in the European Union, where it's mandatory for all software that is produced, basically, that secure by design development principles are applied, that you do continuous vulnerability handling, and that you show transparently what are the components that you're using. So thinking of an SBOM here. And the first deadlines are coming fast this year in September 2026. The same applies, for example, if you are building high-risk AI systems, right? In the European AI Act, there are different levels of AI systems of different levels of risk, but depending on what level of AI systems you are building, you also have to comply to use continuous security risk assessment, thinking of the OWASP top 10 LLM here, or to apply secure development best practices that include secure code review and dependency management. And also here the deadlines are approaching fast. And there are other regulations like NIST SSDF when you are selling to the government software. Here the CEO or CISO had to sign self-attestation that they're using the SSDF standards around secure software development and producing well-secured software. This legislation was pulled a bit back, but still we will see more of those regulations that are adding to the challenge of code security. So what is Sonar's approach to this code security challenge? Sonar is adding a unified verification layer on top of the code development, right? On the bottom of the slide here, you see the development teams that are producing code today much faster, right? Either by using their IDEs together with Gen AI, Windsurf, plugins, etc., or agents writing code fully autonomously and are producing code. And now, on top of this, we are adding this layer where we want to quickly identify and fix issues whenever they are produced, right? So that's the security verification layer on top of the code when it's developed. And This is influenced and defined, and of course, by the tech leadership, compliance, and platform engineering teams who want to make sure that the same level of quality for code is applied across the whole organization for every team, the same quality level. And so they can define the standards. What does it mean to have secure code? What are the rules that we should scan for? What are the compliance challenges that we want to address, etc. And that means we are proactively addressing code security, right? We are scanning when code is written in the IDE, whether with GenAI or not, or is written by agents. We are connecting to an MCP server here to be in the workflow when code is produced and that we fix issues fast. And we can also catch issues at CI/CD stage before code is merged. The most important thing is that code is secured and verified here at this stage, because it gets very costly when we get to testing stage, or of course even to production stage later, when security vulnerabilities are discovered by attackers and data breaches and reputation is at risk. So one core product philosophy we need for this approach is to have a high accuracy, right? What you see here is a table of the industry-leading benchmarks that we use to challenge our own solution here for Java and Python. So we have the OWASP benchmark, for example, and we look at what is the issues that we find in this benchmark that are expected, and what are the wrong finding, the false positives that we find, right? And one key thing here to note is that we have an exceptionally low false positive rate, right, which is here at 2% on average for those benchmarks, while if you look at major competitors in the market, even every second finding almost here is a false positive. And this is so critical because if you think of developers using a security solution, they cannot be interrupted in their workflow, otherwise they lose trust in this tool. And also agents shouldn't be misled by false positives, otherwise they spend time and tokens on investigating problems that actually don't exist and can get very confused about this. The second point here is when we are building an industry-leading accuracy, it doesn't mean we are falling short on discovery. You see here our detection of 95% for Java and 87% for Python finds more security vulnerabilities in those benchmarks than all the other competitors here. You can find more of this online. We're very transparent and are sharing those findings also online. So next, I want to show you a bit of the capabilities that we run inside of SonarQube, our security analysis that leads to this impressive benchmark results. So our core technology that we use is static application security testing, right? Static analysis, that means we are not executing your code, but we are analyzing your source code for all types of security issues, over 700 here, and additionally over 1,500 types of reliability issues. Why is reliability important here? Because reliability is closely connected to security. If you look at the null pointer exception here in the screenshot, you will note that first of all, we do symbolic execution. That means we don't find just like a single issue in one line of code, but we simulate the interaction of code snippets and the runtime behavior, what would happen if you execute the code without actually executing it. And secondly, a null pointer exception can leave the application in an unintended state, and that means it can be a security problem, right? In the C++ world, a buffer overflow is a more obvious example, maybe where you have a crash and at the same time a security problem. Also regular expressions, if they run slow, they can be a reliability problem. If you have a denial of service, you have a security problem. So those are closely connected, and we cover all ecosystems and language here and all types of issues. So next to this broad coverage, we go very deep, right? We have our taint analysis where we transform your code base into a graph model, and then we are connecting the dots. We are finding out where are sources, user inputs that an attacker could modify, and where is data that could be modified by an attacker ending up in something security sensitive. So if you think of user input ends up in a SQL query, it can lead to a SQL injection, right? If user input can modify a file path, you have a file disclosure or path traversal vulnerability. If it leads into an OS command, you have a command injection vulnerability, etc., etc. And so we are scanning those code bases across functions and across files to find those deeply hidden issues for all kinds of programming languages. And of course, this is very framework aware. That means we understand the routing of the most popular frameworks, so we can handle those and simulate those interactions. I want to give you a little demo here of a prompt injection vulnerability. So I have some code here in my IDE, VS Code. SonarQube found an issue, and now we can see those flow steps here that basically visualize what our engine is doing in the background. I can open this issue directly in the IDE with a click, which is nice because it then highlights also those flow steps in the IDE, so I can better comprehend what's going on here. I can read about prompt injection and why this is an issue and a problem and should be fixed. And then here I can follow the flow, right? What is the user input? It jumps to the get quote from AI function. I can jump into the next step where I see this parameter is received, user input concatenated in the prompt, and then this prompt gets into the get LLM response function where it's executed with a system instruction. So I have a prompt injection vulnerability here, and you can nicely see what the simulation steps were here of our engine, and then you can fix those issues like all the other issues with an AI code fix, generated and patch it. Okay, so we have SAST, right? We have taint analysis to go deep, and then we also have secret detection to prevent secret leaks. So secret leaks basically means your developers or your agent hard-coded a password, an API key, a crypto key, access token into the code, and now this code should never leave the developer's machine, right? Because once it's in the repository, like a public GitHub repository, attackers can find it and exploit the secret if it's still valid. So what we also have here next to secret detection is actually secret prevention, and we do that by offering a CLI tool that you can hook into your Git commit hooks, for example, and then prevent that secrets actually get leaked because the whole commit is blocked, and you can use secret detection in the IDE, of course. And we do this for over 450 secret patterns covering over 1,000 APIs, very fast analysis, important for the agentic workflow, and very low false positive rate. I'm also going to show you a little demo here with something cool new that we did. We actually built an AI native secret protection, so we are hooking this into Claude Code. I'm going to show you here how quickly this is to install. I'm just running a marketplace command and then install the plugin for Sonar secret detection, and then I'm restarting Claude Code. And then whenever I'm interacting here with my agent, for example, I copy paste something into my prompt, we are making sure with that hook that the prompt is blocked should it have any secret inside. Why? Because if that secret gets leaked to your LLM provider, it is basically a same leak, then it would end up in a public repository. Another example here is if you ask your agent to access files, right? It would typically read the files and send the information to your LLM provider. But here we are blocking this to make sure also that those secrets don't get leaked. Okay, after secret detection, we also have IAC scanning, infrastructure as code scanning. So basically here we make sure your cloud native apps are protected by scanning Ansible code, Docker, Helm charts, GitHub Actions code, Bash shell scripts as well. So finding all kinds of misconfigurations in those scripts, right? That could lead, for example, that your cloud resources are publicly accessible, or maybe you use weak encryption, or your access privileges are permissive, those kind of things. And then, of course, when we detect all those findings, we aggregate them in cool reports and dashboards. So those are security reports you can download, interactive dashboards, portfolios. So you can hopefully see that over time, your trends, you're improving your security, and that you're complying to PCI DSS, for example, or the MISRA standard, or you're applying the guidelines according to OWASP Top 10 for mobile, for LLM, etc. So what I've showed you so far is in our core offering of SonarQube, right? If you're running SonarQube, you will have already SAST, taint analysis, secret detection, and IAC scanning. What we are offering on top of this is advanced security. And advanced security goes a step further to also secure not only your first-party code, but then also the open source code, right? The bottom of the iceberg, if you will, of your application, because you're pulling in a lot of dependencies, and we can also help you to make sure those are secure. So in order to do this, we do software composition analysis. So at the package level, we are identifying, are there any known vulnerabilities? Are there dependencies violating your policies for the right software licenses? And we also just added malicious code detection if there's any malicious package inside your code base. And we support this for all kinds of ecosystems. Of course, you can download an SBOM report and get a nice summary for this as well. And this is also fed into your security dashboards, of course. If you haven't seen this yet, here's a little demo how this looks like. So you have a new dependency risks overview. You see the issues, like here the CVE vulnerability, and then you can read about what's going on. You have different scoring. How exploitable is this in the real world? What is the severity? How can I fix it? What should be the version I upgrade to next, right? What is a partial fix offering of the dependency? What offers a complete fix? And then also, how does this dependency that is vulnerable actually ended up in my code base? Was it a direct chain or a transitive chain or both? And what other vulnerabilities are associated here? So you get a good view of those vulnerabilities. Then we also have malicious package detection I mentioned. So in December we had Shai Halut, right? We see an example here of a package that is infected and that you then should get rid of in your code base. And you can configure your license profiles. That means you can configure what is the policy in my organization for software licenses. Am I allowing copy left, copy right? We have extensive presets that you can use, but you can also on a fine-grained level configure the licenses that are allowed or not allowed. And then you will see in your projects, once you configure those policies, also findings around license violations. So where dependencies used for GPL license in this case, for example. Okay, and then we will get into a little sneak peek on what else we're working on. So there is for SCA, for example, reachability analysis that is important and coming next. And we will also work on remediation. And obviously in the AI area, we are using here also AI internally to support those features. So I give you a little preview on reachability. You will then see dependency risks with a little reachability label here. You can sort them by what is reachable and find out that this vulnerability here, for example, can be reached. That means at function level, we are identifying that in combination with our static analysis, that you can reach this dependency. That means the vulnerable function is actually called in your code base, and this allows you to better prioritize SCA findings. And then we're also working on agentic analysis, right? So far, we looked at SAST, taint analysis, SCA, secrets, IAC that run in your pull request, branch analysis, etc. But we're also working on leveraging AI to detect code issues, for example, logical flaws, right? Logical flaws are interesting because AI is doing a very good job in understanding the intention of developers, right? It's something where static analysis is weaker in. And so we are leveraging this technology, of course, to find various logical flaws. One example is here IDOR vulnerabilities, right? Insecure direct object references, where attackers can iterate and enumerate throughout a number of objects because of missing access privileges and leak information from your application. And I'm going to show you a little preview of this. So we are running here our agent. And the agent uses various contexts from our static analysis, architecture, etc., and is looking in the example code base here and trying to understand what is the authorization model, right? What are all the different controllers that are present, what I could access as an attacker, and then it checks what is the ownership for those controllers and are those implemented in the right way. And once it found some specific examples where it investigates further, it's doing extensive analysis additionally to check, is it actually really an IDOR vulnerability or is it secure? And then we will see here it found for this example 7 of those vulnerabilities and is then producing and confirming those vulnerabilities and presenting the results. And this is how it could look like then in our UI, right? You have those IDOR vulnerabilities where you can then see a logical flaw that we detected with agents. So that's something we are working on. I think this is super cool. And we have already detected several zero-day vulnerabilities in open source code, so this is super promising. So as a summary, where do we stand here with code security in the AI area? So if you run SonarQube, you have one integrated platform. That means you get comprehensive coverage for all kinds of issues, quality issues, security issues, for all kinds of programming languages and code, right? That's all in one platform, all the technologies that cover everything. Then the most important thing is we are starting left, right? We are verifying code where and when code is written, be it a developer, be it an agent autonomously. And then we have the sophisticated analysis techniques that I showed you some of them today, where we detect complex and critical issues at a very high accuracy and at a very high speed. That is super important in the modern and agentic software development lifecycle. And lastly, of course, we have actionable results. So we give guidance to fix those issues and to meet compliance needs that then can be consumed by the agent again to fix things, by the developer to fix things, or by tech leadership to look at the compliance requirements. All of this bottom line to me is that actually you increase your application security by getting issues fixed, right? It's not about just knowing about them or getting everything into a PDF report. It's about sitting in the workflows and making sure issues get engaged on and actually fixed. And I think that's the only thing that actually improves your application security. So SonarQube helps you with that. Thank you for your attention and enjoy the rest of the presentations.